Hello, my name is Sean Murphy, and I am the CEO, CTO, and co-founder of Titan Advanced Energy Solutions. We are a Boston-based startup. Titan was founded in 2016 on the premise to use ultrasound technology to understand batteries and reduce the cost of quality in batteries. In this process, we have developed a very precise way to measure and understand various nuances of the battery, such as capacity, defect detection, and optimization in the gigafactory. Our deployments have been wide across the United States and Europe and soon into Asia. We have partnered with Siemens and Honeywell and Schneider Electric in investment and in partnership for deployment throughout the world. So ultrasound technology has been around for about 100 years and has been used in many different industries, such as the medical industry, non-destructive testing in the oil and gas industry, in the automotive industry, and aerospace industry, and nuclear industry. We are using something that has been more on the lower fidelity aspect of it, and then took it and brought it to the next level and enhanced it in sometimes 2 to 3 orders of magnitude in precision and knowledge. To just kind of describe how this system works is that we have pairing transducers that will send a signal from let's call it left side to the right side and the right side to the left side. And what that enables us is to scan the whole battery in every aspect of the battery and get information of where the defect is in the XYZ coordinate inside of it with extreme precision. Our technology is augmenting certain technologies in the marketplace and sometimes replacing them altogether. When we refer to it as augmenting, we are augmenting OCV, open circuit voltage, DCIR, direct current internal resistance, and capacity measurement. Sometimes capacity measurement is replaced, but for the real fact is that OCV and DCIR is used in conjunction with our technology. What they do not have is they don't have the 3D morphological understanding what the battery is behaving, what the small nuances, because if you have a 2 millimeter or 3 millimeter square lithium plating, that is impossible to see with any type of current technology. And if you have a lower wetting in the top left corner where it's not directly optimized for OCV and DCIR, it will never be seen. So what this technology does is, because it scans the whole battery, you can see all the blemishes, all the nuances of the whole battery and all of its layers. Our technology is, as I said, works well with traditional OCV and DCIR, but a lot of people use CT to understand quality. Now, we compare to CT in one major way. CT generally looks at atomic density, and what we do is we look at molecular density. And molecular density, what that gives us, that we will see things such as gas, we will see nuances in ripples inside of the separator, all this, call it soft tissues and soft aspects of the battery. Versus when you think about CT, it's very good at cathode ruptures, misalignments. Even though we can ultrasound, and we at Titan do that as well, the other big difference between us and the CT is that we can do inline very quickly. Generally, to scan the whole cell with a high resolution takes us half a second and about half a second to process, while this same thing in a CT would take approximately an hour. One thing to consider the amount of development that we have achieved over the last 9 years. Traditionally, when people think about ultrasound, they think about NDT in the industrial setting. So you have a very coarse type of imaging or a very coarse amount of data. Then you go into more detailed is in the medical imaging. But that still is very, very coarse compared to what we're doing. And one thing to really advance the state of the art of the ultrasound, what we did is that we used focus transducers to really have a very, very detailed tomographical map of each individual cell. And so I will talk about this thing first in 2D, so it's going to be in resolution, and then later on I'm going to talk into voxels. I'm introducing concepts that most people that are not in this type of space do not understand. So when you go buy a TV at Best Buy or whatever, or on Amazon, you usually think about 4K is your resolution of your TV. What we are talking about here is that that's your X and Y, and that's how many pixels that TV has. So if you think about a small battery, which is 12 centimeters tall and about 22 centimeters wide, we usually have something like 10,000 pixels. And then if you add the three-dimensional aspects, those pixels turn into three-dimensional cubes. They're called voxels. And then usually that's slicing. And this is where that understanding where we come into and understanding where the defect is and how the overall battery uniformity occurs. This all comes in from this three-dimensional slicing aspect of it. But overall, you're adding about 300,000 to 400,000 cubes of information or voxels of information. And then you add about 80 algorithms on top of it. And then you truly have a physical manifestation or a digital twin of the battery in ultrasound, which is the first time that anyone has done this. And probably for the next couple of years will be the only company who can do it. So to go a little bit further into detail, what this means is what we are always trying to do is recreate reality in a digital format. In what we are doing, we're of course using ultrasound. And just like we said earlier, we're sending a pulse, a well-defined ultrasonic pulse that goes to the battery. It enters the medium of the battery. And as it's progressing through the battery, from layer to layer to layer to layer, it changes its properties. And if there's no lithium plating, if there's no gas, if it's a good, there is a well-known signature, so you can define what a good battery is. So, and then that usually manifests itself such as like on speed of sound, porosity, attenuation, which is basically saying how much energy is dissipating throughout the thing. Another thickness in layers, the speed of sound changes. So from that, we take all of those on each of individual voxel or combination of voxels, and we create the map, a physical representation or the digital teardown of the battery, and then we put it in, define it, and ID each individual. And this is that part of it what we call semi-supervised AI, which we train the AI to understand what a specific defect is. In the next couple of slides, we're going to show you examples of the various defects from a lot of manufacturers across the world. We categorize defects in four different ways. It's electrochemical defects, process defects, mechanical defects, and those mechanical defects are divided by electrode defects and separator defects. And each one of those has other subcategories, which I'll mention in the next couple of slides. So this one over here is a perfect example of what we are seeing. On the top right corner of the slide, you have a heavily lithium plating battery. And of course, this is a very bad thing, because if you have a lithium plating at this level, you will most likely have a nice thermal runaway, which nobody wants to have. But the beautiful thing about it is that the ultrasound really is susceptible of understanding and capturing and detecting lithium plating with high certainty. The second example that we use over here is wetting, because we see the intercalation of lithium or electrolyte, to be more precise, inside of the anode, and as it's intercalating within the battery, we can see and optimize the wetting process, the pre-charge process, and overall production process, so we can improve it not only in reduction of time, but optimization of how much electrolyte goes in individual cells. The third example that we're putting over here is electrodelamination. This one is more what we call a mechanical aspect, which comes across very nicely with ultrasound, and we have seen this thing in pretty much every manufacturer that we come across. And the last one, which is very, very, very difficult to see, but is the separator wrinkle or the separator incretions, and we see them very nicely in prismatic and pouch cells. So this is basically a direct comparison of a CT scanner to a specific cell, ultrasound, a teardown, and under microscope. And this is a very, very exact example of how you take a CT scanner and you scan it for about an hour and you can't see anything of it, while taking a half a second ultrasound scan, you clearly, and with our AI, not only does it see it, but identifies as lithium plating. And then to confirm it, we use teardowns and confirmed it without a shadow of a doubt that that was lithium plating. And then we did a microscope analysis and it says it was lithium plating. So the technology is implemented and being worked on with several manufacturers, and it's truly a revolutionary thing. These are additional examples of high resolution scans of batteries, and you can see in this one is electrode buckling, and this is a common thing in prismatic batteries, that when you're stuffing the jelly rolls inside of it, not every single time is uniform, and when you do that, you can do buckling. Over here, this is a perfect example of how you have separator wrinkling. Now, separator wrinkling, of course, is definitely not a good thing for a battery. At the manufacturing site, this needs to be very, very tight, because that way you're not impeding the flow of electrolyte, because what will happen is you will have a capacity dip eventually, not at the beginning. And so you can see on the top left side of the screen that we are seeing separator on multiple layers, not on just one layer. And the one thing to note about all of these cells, if you look at the bottom left side, that all of them are passed inspection. They went through all of the normal manufacturing inspections, and all these cells have been sold directly on the market as good cells. And this one is actually one of the worst cells that we saw, which we thought it was just a standard delamination, but it was far worse. It was basically the whole cathode kind of got ripped apart and it was delaminated. And it was like, I have no idea how nothing else picked it up. So one of the last slides to kind of think about this one is that we not only do prismatic cells, we work on pouch cells, and in the next quarter or so, we'll be coming up with a new system that is handling cylindrical cells. And so over here we see a clear lithium plating and a pouch cell, and you can see again that swarming, what we call swimming pool pattern, is just a pattern that it comes from lithium plating. And this was cathode misalignment down and anode misalignment up. And in this case, what we're showing you is basically between a 10 to 40 micron misalignment of a cathode, that if you can look at the bottom right corner, you can see it in the CT. That same battery is represented in the ultrasound in the top part of the thing, which we basically clearly see the misalignment of the cathode. One of the last things that I want to showcase today in the defect side is, of course, moisture. Moisture is the enemy of batteries, and everybody's been fighting moisture in various ways. But what we are over here is that one of the ways you can look at it is the creation of hydrofluoric acid that happens after about 6 or 7 days if there is moisture inside of it. And then they have to eat through the separator, and then you have a short. This is what they call OCV survey or ambient aging. Well, one of the things that is really powerful about ultrasound, that this byproduct starts creating gas. So you can start seeing the formation of gas and take those cells out, or you can see the impact of it. Even if it did not eat through the separator, you can start seeing the early etching of the separator and the electrodes. So that way you can take those cells out of production so they don't come out as a warranty back or a catastrophic failure with your customer. One of the other technologies that we have worked with a couple manufacturers is mapping the capacity, or SOH. And what we are showing over here, that what we did for one customer, we had a sample, I think it was like 600 or 700 cells, and we used that and trained the model to create a capacity model that predicted the capacity within 1% error rate, meaning it's 99% accurate, or similar to a cycler at C/2. So let's talk about use cases, because use cases is what drives economic value. And people that have problems, they tend to come to us. Sometimes people don't have a problem, and then we show them the problem, and then we try to help solve the problem with them. But so let me explain a particular use case. And this is the use case of layer misalignment, which I touched upon. And it was basically a prismatic battery that had 2 jelly rolls inside of it, and they had cathode misalignment. And it would happen in multiple lines at different intervals. So there was not a very specific, call it X amount of percent, that it was always the same. It would be from week to week, it would change. And they could never get it down, and they used inline X-ray. They had a whole fleet of CT scanners operating at 5 shifts, huge amount of people. And as the factory was ramping up, the CTs just could not keep up. And so this is where the challenge came from the head of quality and the CEO of the company, of asking, can you solve that? And I know we were sitting there was a bunch of them at the table, and they really had a serious problem. And I was like, we think about it, I was like, okay, kind of physics can do that. And we were like, do a quick on the whiteboard calculation. And we say, you know what? I think we can do it. Send us 100 cells with these defects, and then we will do it. We'll do a really, really thorough analysis of it and see if we can do it. We came back to them within 2 weeks and saying, yep, I think we can do it. We have a path. And it took about 6 months from concept to productization to at a pilot level, and another 3 months for full production. So from a crazy idea from the head of quality and the CEO to a fully fledged service that basically gave them 1 part per, it was 2 parts per million that would be at the error rate, meaning, because we do calculate everything at false positives, false negatives, and our false negative, meaning a bad cell will go through that we don't detect, it was 2 in 1 million. And of course they don't produce 1 million cells, so basically our system was bulletproof for them. And so the customer was really, really happy because we eliminated something they were just inherent in their design that they could not change, and they could not figure out the variables within the manufacturing process. So the process still produced cathode misalignment down and anode misalignment up, and our system was there and perfectly captured every single one of their cells and solved their solution that their customer on the end, the battery manufacturer customer, they demanded our system runs 24/7 for every single battery that is going in there, because they did not want to have that risk of a layer misalignment within their systems. So we not only got the approval of the battery manufacturer, but the end customer OEM, and we were certified by the end customer as this thing is even better than the CT, because there was human errors associated with the CT scanners. So now that you have seen some of the examples that we went through, what are the defects that we see, how do we work with it, one thing that we should always mention, that there is a good cell, and we see a good cell, and we can define what a gold standard is, and then you can set these thresholds. So that's something that we did not mention in the prior slides, but it is something that the algorithm understands, and we understand with the local battery manufacturer or inbound inspection what a good cell is. But generally what we do is, depending on if you're a pilot factory or production factory, what we do is we have two solutions for our system. For low production, we call this the Titan IonSight pilot system, which basically is between 2 to 3 ppm and can scan the 2,000 to 5,000 cells a day. And it has the same resolution, has the same kind of capability as the industrial one. This just means this is where we create our base algorithms from. The next one, of course, is the one that we worked very hard starting at the beginning of 2024, and we deployed our system in October of 2024, and it was running at full capacity, and it was processing all these cells with all these features. And this is one of the greatest achievements of our company, that we can have multiple arrays detecting multiple defects and multiple, call it, things that the customer wanted, all within half a second into a second per cell. In 2025, what we are embarked right now is all the lessons learned that we have learned in the last couple of years, and in our first operational full production inline systems, we are modifying and upgrading our systems. And so we have optimized on size, we have optimized on the time of deployment integration from about 2 months from integrated in the factory to about 4 weeks. We have optimized and reduced the amount of time for the algorithms to be developed, and it's designed for pouch and prismatic equally and very easily to do it. We as a business, of course, everybody's going to ask, so what is your business model? How does this thing all work? Well, we developed this technology not to sell our equipment, because even if we would give it to the equipment to someone, it would take them years to make sure because there is many aspects of it. So our business model is a full turnkey solution. We will work directly with the battery manufacturer or inbound inspection people, and we will provide the full service, turnkey service of a solution of telling them what is a good cell, what is the defects, identify the defects. And not only would tell them that these are the defects, but our AI models, because we have worked with so many different manufacturers and seen so many different cells, we can give them the recommendation how to improve their processes, how to avoid mistakes, and how not to have additional defects in their production. So when we size that up, what we do is we have what we refer to as services. You have a conformity service, you have a capacity service, you have a layer misalignment service, you have, let's say, call it a gas detection service. All of these services are bundled or separate depending on where the manufacturer is in their call it life cycle. If you are early stage European battery manufacturer, you have certain amount of problems. If you are a late stage, meaning a mature manufacturer that has already sold millions upon millions of batteries to top tier OEMs, you are looking for a Six Sigma and beyond in quality, and so the services are slightly different. So Atlas 2, besides the aspect that we designed it to work for a smaller footprint, for a more flexible Asian line, what we have done is we created it so it can be used for inbound inspection. So when you look at the market, how it looks right now, meaning there's about 4 terawatts of battery being produced every year, but 80% of that manufacturing capability is in China. Now, of course, there's the big names such as CATL, BYD, but there is many other ones that are not. And if you are an American, a European manufacturer, there is a lot of information that you don't have about these manufacturers. You can have some, especially if you're a small, mid-size, a smaller company, you don't have the capability to go and send a team to China to evaluate the factory to see these are the right batteries that I need. But you're more relying from other sources that these are. So that can be overcome for a very, very small fraction. And this is what Atlas 2 provides. Atlas 2 provides that it will be on the forefront of inbound inspection. And we think about this thing in 4 different kind of value streams. One of the value streams is if the system, if you're a pack integrator or you are a manufacturer and your packs are being integrated in China, what we would do is we will probably do this thing with one of our partners such as Siemens or Honeywell, and we will set this thing up at a secure facility close to the battery manufacturer. We do the inspection and provide you what are the ideal batteries that you need to use for your pack integration, cell balancing, and everything else. So you get a total quality control at the point before you integrate it in the pack. So that's your stream number 1. And so that way, when you get your pack that's coming to Europe or United States, you already know that you have a birth certificate, so to speak, of this pack or this individual cell. The second stream is that you are purchasing cells and you're going to integrate them all inside at your facility here in the United States or Europe. And you're an OEM. So and you're not manufacturing the cells in the United States, the cells are manufactured in Asia and they're being shipped. And so what you want to do is you want to have that same type of quality of understanding that every cell is good, every single cell has the same kind of balance. Also, when you're putting your packs together and your modules, they're perfect. And that's an easy way to do it at your facility because the footprint is small. It provides all the information. There's a data fusion. It creates a call it inventory list, and you know exactly what it is because you're creating a birth certificate. Again, the same thing is for if you are ESS, similar to the OEM, there's no difference about it. And at the same time, we're saying to other people in China and to other people in Asia, you know, we can do this thing over there and we can have a secure facility. And the reason why we're saying this secure facility is because the advancement in this technology is so high that we don't want any copycats to go there and start reverse engineering our technology, because right now we have a 2 to 3 year lead against any people out there. Our system provides ultra high resolution in real time. And that is the advancement that we're talking about over here. The other aspect of it is a versatile application. And when we say versatile application, is that we have many services that we can offer. And with this thing, you don't need to have 10 services, you can have 3 services. The last aspect, our cost is very low. And one, it's not a CapEx cost, it's an OpEx cost, but compared to the cost of the battery, compared to the cost of a recall, or the warranty, or installing cyclers, it is fractions of what that costs. And the last part of it is that it's all AI driven. Because we were able to be scanning batteries in the last 4 years, we have petabytes of data that we can create large language models of batteries and recreate reality in ultrasound and recreate AI models that will bring it to the next level.